Hello, everyone. Thanks a lot for the introduction. And as you said, I'm a professor at University of Washington and a research director at Allen Institute for AI. And today I would talk about some research in my lab at University of Washington and also at Allen Institute for AI. Okay. We have witnessed great progress in natural language processing across many applications. Usually, in the field of natural language processing, we measure progress toward external tasks or applications, tasks such as question answering, textual entailment, and many more. Usually, in NLP, short for natural language processing, here is the common paradigm that a lot of people use these days. We have access to large collection of pre-trained language models that we started naming them after Sesame Street characters. And then these are being used as encodings and representations for text. Then when we want to adapt these language models to do some tasks such as question answering, we do different techniques. One specific technique is called fine-tuning, when you are looking at the collection of annotated data specific to one particular task, use it to train your machine learning models that are now able to do those end tasks. Basically, by doing those tasks, I mean building a system that can map the input X, which can be text, which can be a question, and so on, to some output Y that is able to, for example, generate an answer to a question. This way, we have made a really strong, amazing, specialized model for particular tasks. For example, we have good models for tasks such as sentiment analysis, where it tells us what is the sentiments of this particular sentence, or answering questions or translating. But these task-specific models, it's really hard to make them generalize to tasks that haven't seen before. Okay, what we want is something like this, to have an AI model that can do many of these tasks together. In particular, we want to have an NLP model or an AI model that not only is able to be evaluated and perform well on tasks that are known on NLP, but they are also good on tasks that we hadn't known them before, right? A task like negotiation strategy detection, okay? But how do our tasks even know what that or what the definition of the task is? What we like to be able to do is to make an AI system that can do tasks that even is not in the collection of known tasks before. By defining those tasks in terms of natural language for our AI system and then ask them to follow those tasks. Okay, let's see if humans can do it. Look at this sentence. Person X yelled at person Y because blank was so upset about news. You can do multiple things here. If I ask you to answer this fill in the blank question, you will answer this question, tell me person X was so upset. I might ask you to do something different, like modify this fill in the blank question that the answer changes from person X to person Y. Then you can say something different, like person X comforted person Y because blank was so upset. Okay, we have evidence that humans can do these. Basically, these were instructions given to our crowd workers when a group wanted to collect one NLP data set. Okay, now here is our grand challenge in my lab at University of Washington and Allen NLP at AI2. We want to challenge the current paradigm in NLP and build NLP models that can carry out complex NLP tasks, especially when training data is scarce or when it requires complex reasoning. Let me give you some examples. We want to make systems that can answer questions like this. What percentage of the Washington state budget has been spent on education over the past 20 years? In order to answer a question like this is super challenging. It's not like you do Google search and then you can find the answer here. But you can start from there, retrieve the pages, the figures, the diagrams, and so on that contain portions of the answer, okay? Then you need to comprehend and understand all those details that are going on in these complicated graphs, complex text, and so on. Combine all of them, reason about them, and realize now you want to answer this, form this equation, and then answer this. This is our end goal. Or we want to be able to make systems that can verify scientific claims and then argue if they are supported or refuted. For example, let's look at this scientific claim. ACE2 receptors are involved in coronavirus infection. Again, we need to cross-reference it to a large collection of scientific background knowledge, knowledge bases, the abundance of papers that are being published about COVID-19, the research corpus, and so on, and then realize there is a statement like patients that were treated with this drug experience a reduction in symptoms. And then by kind of integrating all these, we realize, oh, yes, this scientific claim is being verified. Okay, so this is our mission. We want to build a novel model that can carry out complex NLP tasks by reading their descriptions. You might ask, let's use this famous model GPT-3 from OpenAI, where we can pass a few examples to describe the task, and then ask them to kind of answer questions, to do scientific claim verification, and so on. This is super convenient, right? But there are a lot of issues. One, transparency. We have little understanding of why GPT-3 works. It is super costly. The model is giant, right? It has more than 175 billion parameters, and it basically has little understanding of what data it has been trained on, and so on, okay? And one other thing is, in the in-context learning setup, we are using the model as is at inference time. We might be able to do some light training, additional training at the inference time to be able to follow instructions. Another end of the spectrum is fine-tuning, where we're going to look at the annotated data for a given task and then try to build models and adapt our language models to do those end tasks. First, this might be infeasible for some sort of new tasks that we have no idea what they are. We just have a short description or just a few examples. This way, we can collect data only for a few tasks, not like a super large variety of tasks that we are dealing with when we are dealing with natural language. And then at the end of the day, the model that we are building this way will be too specialized to do those end tasks. And it's very hard to be able to generalize them beyond those specific tasks. So this is our goal. Instead of out-of-the-box GPT-3 model, we want to learn a new task from related NLP tasks that exist in our current repository, and then we want to do it at much lower cost. Okay, basically we want to have a model that looks at a large collection of tasks that are available to kind of researchers in NLP, do meta training, like this high-level training, and then at inference time, we can keep the model frozen or lightly tune it. When the new task description comes in, we would be able to kind of perform this new task. Okay, let's see how we want to do it. Here I would explain two recent work in my lab called Supernatural Instructions and Meta in Context Learning. First project. This project is led by my amazing students and colleagues and my team members at the University of Washington and Allen Institute for AI. Supernatural instruction is a meta data set that includes more than 1,600 NLP tasks. These tasks are across 76 broad categories, and we have annotated instructions, which are like complex definitions of how we do those tasks, and instances for those particular tasks. This collection is contributed by 88 NLP volunteers. And basically, using this data set, we are able to, one, evaluate if models can generalize beyond NLP tasks, and also we are able to see if we can build models that can do many of these NLP tasks. Okay, great. So I'm just wondering if you are seeing my screen, updated screen. Yes? Okay, I can continue. Perfect. Every instance in my domain now looks like this. A task instruction where, actually, let me also look at the questions to see if there are new questions. I'm learning. Okay, let me continue because I'm sure I'm not having much time. Okay, so let me start from this project, Supernatural Instructions, where it's a metadata set consisting of more than 1,600 NLP tasks across 76 broad categories. And every instance now in our data set looks like this, where we have a definition as how the task should look like, a set of positive examples of explaining the task, and also a bunch of negative examples of telling how the task should not look like. And some evaluation instances where the input is like the textual input, and then output is the label, the final outcome that we are looking. Now, we have set aside a collection of 120 tasks across 12 categories in NLP, where we want to evaluate our AI models. This is our first model designed to do a good job in our metadata set. Basically, we want to build this model that learns tasks from instructions, okay? In the first stage, which is the multitask training stage, we sample a task T, then we transform our instances in this form. Like we have instruction plus input X, and then we map it to the output Y. And then at the training, we want to maximize the likelihood of predicting the output Y given X plus instruction. And then at the inference time, we keep the model frozen, and we want to find out what is the most likely Y corresponding to instruction plus X. So this way, we have trained our model across 64 categories and for more than 750 tasks. And then we evaluate the trained model on 12 categories in the kind of evaluation set of 120 tasks. Okay. This way we build we call it TK Instruct model, which is built on the T5 model. First positive result, which showed, and it was aligned with our intuition, that adding more and more tasks and adding to the diversity of tasks is actually helping with improving performance on the end task. Like if you look at this figure, the x-axis shows the number of training tasks, and the y-axis shows the accuracy. And as we increase the number of tasks, the accuracy is increasing. Here are our results, the result of the TK Instruct model. The blue, the orange, and the green bars are the baselines, showing kind of that the metadata set, that the supernatural instruction data set is challenging. The red bar shows Instruct GPT model, which is basically using the off-the-shelf GPT-3 model. And then the purple bar is the result of our system TK Instruct. First, it's very interesting to note that our TK Instruct outperformed GPT-3 in 10 out of 12 categories, where it only uses 11 billion parameters compared to 175 billion parameters of GPT-3. One other important thing to note that is we are still lagging performance compared to fully fine-tuned model. Like on average, our model achieves 62%, where the kind of fully fine-tuned model achieves 74% accuracy, which shows a lot of room to improve for the researchers in this area. This is a demo, like our demo is available through the LNAI website. We have asked our system to write a story about Yizhang Wang, the first author of this paper, Oren Etzioni, the CEO at the time of AI2, and then Bitcoin. Now, our system has hallucinated that Wang is an associate professor of computer science at the Princeton University, and it has basically founded this company with Oren Etzioni, and it's like basically our system is able to predict the future. Okay. We have done multiple new steps on top of our current systems, where instead of just do multitask training over the large collection of tasks that is available, we have tried to do more data efficient methods for multitask learning. We have shown positive results there. Also, we have tried parameter efficient fine-tuning methods instead of in-context learning at inference. And finally, and we've observed performance gains. Also, we have tried more advanced meta-learning optimization method, but we didn't see any kind of improvements here, which is very interesting to note because usually using much more complex methods, like for example, mammal style optimization in the meta-learning approaches, it's really hard to achieve good results with those because they are adding unnecessarily complications to our models. Okay, one more recent work, we have tried to explore areas for efficient and modular multitask training approaches. In particular, we have looked at the collection of our source tasks, let's say task 1 through task 3. Then we have encoded these through prompt tuning and obtained task vectors. These task vectors are obtained, and we call them kind of these source prompts, the prompts that are encodings of these different tasks. Then we have aggregated these prompts or these vectors by through some sort of attention mechanism, and then finally integrate them with the final target task and show that now we have achieved better performance compared to just few-shot transfer learning method. And this has shown a step toward more modular task adaptation methods. Okay. So now let me move on to our next step, which we have explored doing a meta learning approach for learning new tasks from only a few examples. This work has been led by my amazing student, Seiwon Min, and it has been published at NACL 2022 and EMNLP 2022. Okay, so our main intuition is that it's really helpful to learn from a large collection of tasks that are available to us. And then many of the NLP tasks are somehow related to each other. Okay, so for example, here is a group of NLP tasks. Okay, and we have different kind of variations of these tasks across many data sets that is available to us in NLP. Okay, and also we have seen some good results already using our multitask learning approach when we have zero-shot training or we are looking at instruction. Okay, so here, this is our strategy and our question. We want to see if we can meta train a model to be a better in-context learner. What we do is the following. We look at a language model that is a collection of a few transformers, At this stage, at the meta training stage, it is fully trainable. We're going to look at a large collection of NLP tasks. For example, these are some examples like Squad, AG News, SST2. These are like data set names that exist in the NLP domain. Okay, and there are many more. Then at the training stage, we teach our model to learn a new task only from a few examples. And then at the inference time, the language model is no longer being trained, right? The parameters are kept frozen. When a new task comes in with only a few examples, now we want to see how our model would operate. Okay? At both of these stages, we have in-context learning objective, and our meta training basically has taught our model to learn a new task only from a few examples. These are the details of our approach. At the meta training stage, we sample a task T, we sample instances, and then we do the optimization. And at inference time, we want to find what is the most likely one. Let me go into a little bit more details. We're going to sample a task T, okay? For example, AG News is just one example of the task, okay? Then we would look at the examples, like K+1 examples on this data set. How do we look at these tasks or these K+1 examples? We set aside the first K example as training data and the K+1's example as the test instance, okay? We have this fully trainable language model that looks at that K example that are acting as training example and then the K+1s that is acting as our test example, okay? Now, our fully trainable language model knows how to learn a task from these K samples. Then at inference, when a target task comes in, which has the input instance X, we explain the task with this X1, Y1 through XK, YK, which have these K examples. Then we concatenate them to the input X. But now the good news is that our language model at this stage knows how to follow the descriptions of the task only with these X1 through XK. Okay, it can predict the final outcome Y. So when I explain this model, of course, our results are good. You're seeing too many bars here, but I have categorized them in these three settings. One, you just using raw language model, the blue bars, which overall you see these are much lower than our setup, that our kind of meta learning stage in the red bars. The green bars are the baselines where they are not looking at any examples. And finally, the best model is the channel version of our meta in context learning, where I'm not going to go into the details here. Okay. One important thing to note again here is that we have compared our meta in context learning model that you are seeing, it is highlighted in red, with GPT-3, which uses 175 billion parameters. And as you see, our model achieves a stronger result compared to a model that is much larger. Okay, so I have 1 or 2 more minutes. I know I'm almost out of time. I just wanted to kind of wrap up with understanding and explaining why our approach has worked. First, this is aligned with our intuition that we want to learn from a large collection of tasks that are available to us. Second, we want to dive a bit deeper into understanding what is going on behind the scenes in the in-context learning, okay? There are multiple factors. Oh, I still have more time. Good, so I don't need to rush. So we have multiple factors. The first one is input distribution, okay? So for an input instance X, for a given task, we want to see what is the distribution before input instances, like what is the distribution around the input Xi's, okay? The second important component is the output distribution, right? So for example, if I'm looking at the task of classification, I want to see what are the space of possible labels y1 through yk. Okay, and these are very important. And our meta training stage actually kind of encourages more about, okay, how the input distribution looks like or how the output distribution looks like. So these are really two important factors. Okay, there is another interesting component here, which is how the input instance X, how the output label Y is aligned with the input instance X. Okay, basically the input output pairing. There is one very interesting observation that we have explored in our very recent paper of rethinking the role of demonstrations, what makes in-context learning work. We realized that if we actually replace the gold labels YIs with random labels, that some of them could be wrong, the accuracy doesn't drop much, meaning that in these few examples that are passed in the in-context learning, they are actually not contributing much to the final results of my language model training. Okay, and interestingly, our meta training approach actually kind of ignores this input-output pairing and then advocates for ignoring it even more. That's why we are thinking basically why our meta in context learning is achieving much better results compared to just using kind of input and outputs. Okay, so we have done more analysis that you can take a look at our paper. One important comment is the number of meta training tasks is really important. Like if you add more and more meta training tasks, our results are being improved. The diversity of meta training tasks is really important, right? So for example, if we only add more and more tasks in one domain, like question answering, we don't gain much. But if we kind of add a variety, like question answering, textual entailment, and so on and so forth, we are gaining more. Data that have higher quality, they matter a lot, and adding more and more data that have that are being better annotated are really helpful in our meta learning stages. Okay, like for example, if we are looking at the tasks in glue or super glue, which are kind of famous go-to benchmarks in NLP, and if we have looked at their collections, those are really helpful. And then finally, when we have used adversarially made data sets and we have included them in our meta learning stage, we didn't see much gain. And kind of thinking about this idea that when we are artificially collecting these data sets, they are not that helpful for our end task. Okay, so here I want to wrap up so I can also start answering questions. In this talk, I talked about two recent kind of projects in my lab that both focus on how to build NLP models that can carry out a new task, especially when training data is scarce. In the first setting, supernatural instruction, we want to learn related tasks from task descriptions. And in the meta in context learning stage, we wanted to learn a new task when we were just given some demonstrations or only a few examples. Okay, thank you. With that, I'm opening it up to questions. Sorry about the first part of the talk that I didn't realize my slides are not moving. Okay, thank you. So I'm happy to take questions. Okay, there is a question. Let me read the question. Is it helpful to take a model trained in the same domain for a different task and just use it as a starting point for fine-tuning in another task in the same domain? This is an excellent question. I would say both yes and no. So we have some very recent work that we have shown that we can think of different task vectors in a domain, that where we define a task vector is kind of the direction in which a task goes from a pre-trained model all the way to the end task, right, to the fully fine-tuned model. Okay, so now if we have a good direction to start with, then potentially pushing the optimization in that direction would be helpful to do a better job in the final fine-tune. Okay, so if when we train a model in the same domain, like by same domain you mean, for example, news type text, right, and we want to evaluate on the news type article, then we are potentially moving in that direction. And then when we do that, then it potentially can help us achieve the fully fine-tuned model. Okay, but if there are domains that, like, we are sharing similar input distribution, but for example the final task is very different, and then when you train, you start your training and it's in a very different direction than your final model, then this type of fine-tuning probably won't be that helpful. But this is very interesting question, and I'm happy actually to ask one of my students to kind of evaluate this and see empirically what type of tasks are helpful for task transfer and faster fine-tuning. Okay. Can this method be generalized beyond NLP into other domains? Yes, actually. And again, this is super interesting question. We are also exploring similar ideas in the domain of computer vision, and we are seeing relatively similar results with some caveats where, like in the computer vision, the variety of tasks are less compared to NLP, right? Many of these kind of tasks in computer vision are around kind of object detection and so on. So it's not like we have this super large collection of 1,600 data sets. But yes, we are seeing kind of relatively close results there as well. Good. Another question. Okay, yeah, this is actually a very good question. Can we train a model that first train on lots of data and then train it on scarce data? Absolutely, yes. Again, this is an ongoing collaboration with a group at Facebook AI Research that we are exploring this idea where, let's say we have a collection of different domains and somehow we know kind of the labels of domains, like we know this is news text, these are like kind of conversations, these are scientific text and so on. And we have annotated data, larger scale annotated data in each of these domains. Let's build models and train models for all these particular domains, okay? And then let's start integrate them and then kind of combine them all together. At the end of the day, we would have a model that can work on a big collection of those, okay? And we are trying multiple strategies like kind of weight space ensembling, where we are looking at the average, we are looking at averaging the weights that we are achieving from all these models. And then once we have this final model, we want to now move on, ask questions or do some tasks that we only have a few examples, right? Like in the kind of so-called few-shot evaluation or zero-shot evaluation. And with some of the earlier experiments that we are doing, we've already observed good results in that domain. Yes, thank you.